Yep. Yep. You're right. All right. So we have, you got to get this memorized. And by using these, you'll have 85, 90% of it memorized. Probably another 10% you're going to actually have to actively memorize it and look at it. But it's not like you're going to need to know this tomorrow. This first one is called the power series, because we get the powers. If you have the sigma notation, here's sigma notation. It's all the powers, so x to the n. We're going from 0 to infinity of x to the 0, x to the first, x to the second, x to the third, and keep on going. So there's the sigma notation for the series. This is the convergence. And really, the definition of absolute value says that instead of writing this, we can write -1 is less than x is less than 1. What that means is this series converges 1 unit away from where it's centered. And I made a little Desmos of this. I think this is really going to help you understand what that convergence means. I hope anyway. What do I have highlighted? I don't want that one yet. I got the 1 over 1 minus x highlighted. So there's the graph. And we're centering at 0. These are, if you look at the table, it's Maclaurin, not Taylor series. Maclaurin centered at 0. So we only care about a little piece of this graph. Here's the series up to x to the 7th. And what you'll notice is it's good until it hits about 1 unit away. See 1 unit to the left, how it's diverging from it. It's not, it's getting much worse. And by the time you're 2 units away, it's ridiculously bad, right? It would be horrible. Over on the right side, it starts to fail. I mean, you can judge. It starts to fail in this area somewhere, but it's within 1 unit from the center, which is 0. And so that right there, inside the shaded area, it'll converge. It'll get closer and closer to it the more terms we put on. But outside of that, it'll always get bad. You can put in 1,000,000 terms if you want. It will get bad outside of that shaded region. Does that kind of help understand what we're talking about here? Good, because I spent a lot of time making this. 1 over x plus 1 over 1 plus x is the alternating power series. And it just alternates signs when you put that plus down at the bottom. Now, if we're going to write the sigma notation, we have -1 to the n, so that when we plug 0 in, it's positive. Starts with positive. Plug 1 in, that's negative. Plug 2 in, that's positive. Plug 3 in, it's negative, and so on. And then you just have x to the n as all of the terms. The x, x to the 1, x to the 2, and so on. E to the x, we've done that. All of the derivatives would be e to the x, and we're plugging 0 in each time. So all of the coefficients are going to have a 1 in them. And then the coefficients also include the factorials. So there's your power. There's your series for e to the x. So it's x to the n over n factorial. And there's a 1 there, right? 1 times all those. But that's what e to the 0 is every time we do the derivative. This converges for all reals. So that's just a comparison. Let's see what this looks like very quickly. What does it mean to converge to all reals? Well, first of all, this one only converges within that shaded region, the alternating power series. Here's e to the x, and here's that exponential shape that we're used to seeing. Looks like I went to x to the 7th, and it's pretty darn good. Look how it's very good, well past 1 unit away. And you have to go pretty high up to see that it's not very close. You gotta go way up here to see that it does eventually fail. These are just approximations. So it does fail, but it took a while. And it's certainly beyond 1 unit. So this will converge for all reals. It'll keep widening out and getting better and better as we add on terms. Sine of x centered at 0 is an odd function. So it does alternate, but we have all the odd powers. There's the fact that it's alternating, and 2n plus 1 is odd. Multiply anything times 2, you get an even. Add 1 to that, now you have an odd number. So here's the sigma notation. This is called the nth term. And you can see there's an nth term here, nth term, and then you use that nth term in your sigma notation. The difference is we're actually saying where we're starting. We're starting at 0 here. So there's the alternating piece, and then x to the 2n, x to the 0. If you plug 0 into 2n plus 1, you get 1. You plug 1 in, you get 2 plus 1 is 3. You plug 2 in, you get 4 plus 1 is 5, and so on. And then it's odd factorials in the bottom as well. Cosine, when you center at 0, is an even function. So you have all of the even powers. Now these converge for all reals. And sine and cosine get incredibly accurate, incredibly fast. The rest of them don't quite match up to sine and cosine. Natural log of 1 plus x ends up being x minus x squared over 2 plus x squared over 3 minus x squared over 4, and so on. Because almost everything cancels in the factorial except for the very last number. Here's your nth term, and then here's your sigma notation for that. Now, starting with 1 here, if you're going to start with 1 because that's power of 1, if you go negative 1 to the n, that would start with a negative. So they just offset that by n minus 1. Now when we plug 1 in, we get a 0, and that means the first term is positive. So they're like, I really don't want to start with 0 here because that's not what the powers are doing. They're like, well, let's start with 1 and then offset that by 1. What would it look like if we did start at 0? Would negative 1 to the n be okay? Would that give you a positive? Negative 1 to the 0? That'd be okay, wouldn't it? I need x to the first. So x to the what? N plus 1, right? I just need to add 1 to that. So this would be n plus 1 over, well, I need that to be 1, right? But I'm plugging in 0. So I just have to make this n plus 1. You can start with any number you want. Any one you know. You can start with 107 if you want. But I wouldn't do that. Don't make it too complicated. We usually start these with zeros, or we start them with 1. Sometimes 0 makes more sense. Sometimes 1 makes more sense. And according to the author of the book, it looks like this author is looking more at the powers than they are the coefficients. Make sense? You can start with anything you want. You just have to adjust it to fit so it works. All right, inverse tangent. Oh, this is interesting. It fails at 1 unit to the left, but actually converges 1 unit to the right. Which one is that? Natural log. Click, click, click. So right there. Let's get that other one off. Off. Let's turn that off. Turn that off. So it's good in the gray area, or whatever color that is. What is it, green? I'm colorblind. Is it green? Green, okay. Anybody else colorblind? It sucks, yeah. Because I can look at a color and I go, well, I think it's this, but it could be others. It's kind of weird. So it fails at 1 unit to the left, but it will slowly converge to 1 unit to the right. You can see there's still gaps because I've only put in a few terms there. Went to x to the 11th, so you can see how slow this is compared to sine and cosine. It converges very slowly. But it does. And then inverse tangent converges on both sides, one to the left and 1 to the right. Here's what I want you to do. If you're right-handed, take your left hand and cover up the chart. If you're left-handed, take your right hand and cover up the chart. And then answer that first question. You can cheat if you want, but I don't want you to. I want you to be able to do this without looking at the chart. You have to have this memorized. AP expects that, not me. Don't blame me. AP wants you to memorize this. If it was up to me, I'd give you the chart, but it's not. Students will be able to find and use Taylor-Maclaurin. Find the 6th degree Maclaurin polynomial for f of x equals cosine, used to estimate cosine of 0.1, and we already know that it goes to 10 decimal places because we've done this before. But we're not building it. We're not doing all the derivatives if we don't have to. That's the difference between what we've been doing so far and today. Today, I just want you to be able to do this. P sub 6 of x is, all right, it's an even function when it's centered at 0. So that means we have x to the 0, x squared, x to the 4th, and x to the 6th. So it's an even function. I need the even powers. You just have to remember that it alternates also. Sine and cosine alternate signs. They're an alternating series. So you can uncover it if you want now. And now you're usually asked to use it in some sort of way. So we want the polynomial of 6th degree, and we're estimating 0.1. So 1 minus 0.1 squared divided by 2 plus 0.1 to the 4th divided by 24, and then minus 0.1 to the 6th divided by 720. So if we go cosine of 0.1, you can see it's accurate to at least 10 decimal places, maybe more. Now, like I said, the difference between what we've been doing so far is I want you to just be able to write it. You have to memorize this, because you might be expected to do this in some sort of fashion on the test. All right, cover it up. Cover it up. Do the next one if you can. If you got to cheat, be big cheaters. Now, if you got to look right now, I mean, that's fine, but eventually we can't. We're going to have to be able to do this without looking. Now, we're doing this without building it, but that doesn't mean you can't think about building it. About how did we build it? We plugged in 0. Then we took the derivative and plugged in 0. Then we took the derivative and plugged in 0. But the derivative of e to the x is all e to the x. So every single, the value of all the derivatives for this, we're centered at 1. So all the values will be not 1, but e, right? E to the first. All the derivatives will be e, and we're plugging in 1. So all of the derivatives are e. So p sub 4 should be e plus e x minus 1 plus e x minus 1 squared over 2 factorial, or 2 if you want. X minus 1 to the 3rd over 3 factorial. X minus 1 to the 4th over 4 factorial. The tests are generally built so that if you have to work all this out, if you have to take all the derivatives and then find the values, you're probably going to run out of time. So it's built so that you know how to do this without building it. All right, so p sub 4 of 1.2. The good news is all of those subtractions will result in just a value of 0.2. Now there is an E button on your calculator. It's the second function of divide. So that makes it go a little quicker. You don't have to put e to the first every time. And that's going to be times 0.2 when we do the subtraction. Plus e times 0.2 squared divided by 2 plus e times 0.2 to the 3rd. I think I'm on the 3rd. Divided by 6 times 0.2 to the 4th divided by 24. That's it. That's it. Now, if I let's test to see how many decimal places we're off. E to the 1.2. 1, 2, 3, 4. We're accurate to 4 decimal places. So 3.320109425. How many decimal places? 4 decimal places. It doesn't quite stack up to sine and cosine. It takes a little more, a few more terms to get real accurate. But I don't know. I mean, how many things, how many actual applications would you have to be accurate to more than 4 decimal places, right? That's pretty darn accurate if you're looking at kind of measurements or any kind of engineering. I don't know, that's pretty good. Well, let's apply it to e to the 3x. Let's think about the derivative of e to the 3x. What's the first derivative? 3e to the 3x, right? And we're plugging in 0 because it's a Maclaurin. So the first derivative would be 3. What's the second derivative? 9e to the 3x, right? And then 27e to the 3x. And then 81e to the 3x. So it's just powers of 3 is what you end up with when you're centering this at 0. So p sub 4 is 1, because it's the function value. If I plug 0 in, we get 1, plus 3x plus 9x squared over 2 factorial, plus 27x to the third over 3 factorial. We're going to the 4th degree, plus 81x to the 4th over 4 factorial. Now, this is, I'll remind you one more time, I don't know how many more times I'm going to say this because hopefully you just kind of know it. It is over 0 and 1 factorial. So it's not like we start the factorials later. We start them right away. But we just don't write those two. Find a Maclaurin polynomial. Oh, that's it. That's all it asks you to do. There we go. But let's start looking at sigma notation for this as well. I don't know. What do you want to start with? You can start with anything you want. What seems reasonable for this one? 0 or 1? 0, yeah, because we have x to the 0. We not only have x to the 0, we have 0 factorial. So we're going to go n equals 0 to 0, 1, 2, 3, 4. We'll worry about infinity later. But if you happen to put infinity up there, I wouldn't count it wrong, because that's kind of where we're headed anyway. 3 to the n, right? 3 to the 0, 3 to the first, 3 squared, 3 to the third, 3 to the fourth. X to the n. All the x's are powers of x. Over n factorial. And you can also write it like this. 0 to 4. I'm so used to writing infinity, and my hand just writes infinity. 3x to the n over n factorial. You can do either one of those. Those are both legal in Nebraska. Find a Taylor polynomial of degree n centered at x equals c for each of the following. So f of x is cosine of x. We're going to go to the 4th degree, and now we're centered at pi over 4. Let's talk about that a little bit, because first period, someone came up to me, had a great question, really was. I said cosine is an even function, and so you should have even powers. It's an even function when you center at 0. If I center cosine right at 0, it's a nice even function. It's a reflection over where we're centering it. But if I center at pi over 4, right here, let's see, this is pi, or this is 0, this is pi over 2, this is pi for cosine. So if I move the center over here, now we have a new center. So if I pick a point here, it's not an even function. Not an even function anymore, is it? Not when I move the center of the graph. So now we can get odd powers of it. But now here's a question. Where will it be an even function again? At pi, right? At pi, now if you did the polynomial at pi, you're going to expect an even function again. Where is it an even function again after that? 2 pi, and then 3 pi, and then 4 pi. Anything in between there, anything that's not a multiple of pi, you do not have an even function because you've moved the center of it. All right. He asked me that, so I thought I would tell you right away. This one, I don't think I would do without, I think I would build this one, unless you're real comfortable with this stuff. So we're going to go f of pi over 4. Cosine of pi over 4, there's going to be lots of square root of 2 over 2's. F prime of pi over 4 is negative sine of pi over 4, which is negative square root of 2 over 2. And we're going to a 4th degree, so we got to do a few more. Second derivative, negative cosine of pi over 4. Well, that's another negative. It looked like this was going to be an alternating one, but it's not alternating. Third, sine. Square root of 2 over 2. And when you hit the fourth derivative of sine or cosine, you're back to where you started. So we're back to cosine over 4. Square root of 2 over 2. And that's what we want. We want the fourth degree Taylor polynomial for this. So lots of square root of 2 over 2s, but it looks like it goes 2 negatives and 2 positive, 2 negatives and 2 positives. That's not alternating. So P sub 4 of x is square root of 2 over 2 minus square root of 2 over 2 x minus pi over 4 minus square root of 2 over 2 x minus pi over 4 squared over 2 factorial plus square root of 2 over 2 x minus pi over 4 to the third over 3 factorial. And finally, we got another positive, x minus pi over 4 to the fourth over 4 factorial. There we go. So that one I would probably build. So I'm not saying that you have to do all of these by memory, but some of them you do. Some of you are expected to. And that's all it asks you to do is just write the polynomial. Questions on that one? And the question that the student had first hour, which is a good one, is like, wait a minute, you told me that this was an even function. I did, when it's centered at 0, or pi, or 2 pi, or 3 pi. Anywhere else, it's not an even function anymore. This one, you could certainly do it by L'Hopital's. But if you do that on the test, I'm going to give you no credit whatsoever because I want you to follow the instructions. It's not the answer that I'm more worried about. It's the process that we're looking for, not the answer. So if all it says is find this, if that's all it said, you can do it however you want. So here we have the limit as x approaches 0 of 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial. So we're replacing the cosine with the approximation polynomial over x squared. So now it's all algebra. So limit as x approaches 0 of 1 minus 1 is 0. And then we're going to run that squared through. But instead of dividing by x squared, we're going to multiply all of this by 1 over x squared. So instead of dividing, we'll multiply by the reciprocal, just like we've been doing in the past. Now, if I run that 1 over x squared through, the x squareds cancel, and we have 1/2, or 1 over 2 factorial, plus x squared over 4 factorial. Now we can plug a 0 in, and the answer, the limit is 1/2. Now, without the instructions, I wouldn't use this. You know, if that wasn't there, I certainly wouldn't go, oh, I know the polynomial for cosine. No way, I would do these L'Hopital's because it's 0 minus 0 over 0. So we do L'Hopital's. Limit as x approaches 0 of sine of x over 2x. That's still 0 over 0. Limit as x approaches 0 of cosine over 2. Cosine of 0 is 1. So 1/2. But like I said, I want you following the instructions on the test. If you don't, I'm not going to give you any credit for it. And I think you know that. Suppose that the polynomial is this. And notice how we write it backwards with Taylor polynomials. That's how you build it, by power. Is the second degree Taylor polynomial for the function f about x equals 0. What can you say about the signs of a, b, and c if f has the graph given below? So this is the point 0a. So a must be greater than 0 because we're above the x-axis. If you take the derivative, it's b plus 2cx. Then if you plug in 0, the derivative is b. So b, it looks like it's negative there. We have a negative slope. And then if you take the derivative again, it's 2c. So the concavity seems to be down. So c must be less than 0. So it's all about derivatives there and what the derivatives mean. First derivative is slope, second derivative is concavity. So here a is less than 0. Slope seems to be positive, and the concavity again seems to be down. So C is less than 0. All right, with your table partner. Want to slide over there? Discuss. Do this. What do you think? You can cheat. You can look at anything you want. I think this one you have to build. You just have to build this one. X times 1 over x is 1, by the way. There's a little hint. X times 1 over x is 1. Do A, B, and C, by the way. Do it all. So you need to calculate. Oh, that's not one. Anybody disagree? Anybody spot a mistake I made or anything? I think I got it. What am I on? I got to the third. I need to the fourth. Oops, not times, divided by. That's not it. How is it? No, I don't think that's it. I think I messed up. Let's find out. 1.1 times natural log of 1.1. Yeah, I knew that was wrong. Where'd I go wrong? Oh, times. Is that all? That the only mistake I made? Still wrong. Oh, what's that? It's going to be plus. Oh, I'm all over the place. Minus 6 times. Still not right. Gosh darn it. Come on. I nailed this first and second period. Trust me. Wouldn't lie to you. So 0.1 plus 0.1 divided by 2 factorial. Plus, oh, is that a minus? That's a minus. And then plus 2, and then minus 6. Should be accurate to 7 decimal places. There we go, I finally got it. 1, 2, 3, 4, 5, 6, 7. Yep, there we finally got it. 0.10484116667, 7 decimal places. There, took me a while, but I got it. Questions on this? There you go.